be making a basic sine curve model using Google Colab notebooks. So, uh, uh, introduction to TinyML, making a basic curve using basic sine curve model. So there are certain parts to make a sine curve model. We'll go through this later. Just see it for now. Okay, so TinyML is basically like you can't run a ML script normally on microprocessor because microprocessors are usually very limited in their strength. They are at max about 16 MB of storage, a few kilobits of RAM. So like you can't. There's not much things you can do with the microcontrollers usually. So what we will do is that we will use TinyML. TinyML is like it can run ML on the microcontrollers and use a special processing so that the code is shrunk down. All the learning part is done earlier, and the final model is uploaded onto the TinyML, uploaded to the microprocessor. So pre-processing, the TensorFlow Lite runs the interpreter, then the model is uploaded into the microprocessor, and it handles the outputs. So like, so for handling TinyML, we use a library called TensorFlow. TensorFlow is a free open source software library made specifically for using um, ML on all devices. And TensorFlow Lite is specifically, then the TensorFlow Lite exists. TensorFlow Lite exists basically, wait, TensorFlow Lite exists so that we can run these ML models made by TensorFlow on smaller devices or embedded systems on mobiles and edge devices. So TensorFlow Lite / micro TinyML, this is much more compressed than TensorFlow Lite. So like it supports in C libraries. The model which we make in TensorFlow is converted to TensorFlow Lite Micro. So like you can make this on Google Colab notebooks. You can just import the model and you can just run it on any microcontroller device through Arduino or ESP32. In this case, we'll be using ESP32 later. So how do we solve an ML problem statement? First, we have to like decide on a goal. So like if you want to make a machine, this can record temperature continuously and accurately, we'll just decide on it. So we need a data set to collect the information. So we'll collect a data set from different places. So imagine that we have an inaccurate sensor, for example. The sensor like has a variance of +1 degree, -1 degree. We'll collect the data, what sensor produces, or we'll also collect the true temperature using another sensor. So we'll get two inputs. So we can get a approximate reading basically from the sensor. So we can remove the big errors. So we'll get a somewhat varied error with a varied data which doesn't make sense on normal. It doesn't look like a straight line. It's scattered from one can be above one can be show one reading can show 1 degree more. 1 reading can show 1 degree less. When you plot it as a graph, it looks like the temperature is varying, fluctuating very fast. It doesn't make sense. So we just collect the data set. We'll just clean the few degrees which are too off, like 2 degrees, 3 degrees, 1 or 2 may vary so much. So we'll just clean all the excess data and we'll have perfect data set ready for the model. Designing the model, then we'll design a model which can handle the data. So if you have so much variance or the model is complex, or the function you are plotting is complex, you might need to use a more complicated model than a more basic model usually. So in our sine curve, we'll try with both a basic model and a little bit advanced model, and we can see the differences, what's happening there. So training the model. So like the model itself in it is not useful. So we have trained the model. The training means you'll just run the pre-processed data set, and after running through it, the model will train on every x data. So what happens is that each neurons will have a certain value, the values will be changing. So next part is testing and debugging. Errors may happen. We'll just check that if the model matches the model whether it's underfit or it's overfit. So we can just see. And on the next upcoming sessions, we'll also see how to convert our model, deploy our model, program on our microcontroller, and run it on the microprocessors. So okay, you'll see some terms called flat buffer. Flat buffer is basically comma separated values. So like each model will have weight and biases, right? So these weights and biases are stored as flat buffers. These flat buffers are usually arrays in C files. So these buffers have a faster speeds. You can see like a JSON files takes up to 2.2 milliseconds per operation, but whereas flat buffer just takes about less than 100 nanoseconds per operation. So like flat buffers are much more easier for microcontrollers to handle. So we prefer flat buffers here. So whenever you see flat buffers, it's just a array of long array of storing all the bits of data which are weights and biases basically after we train the model. Quantization is like after training the model have weights and biases. These weights and biases may not necessarily be integers. So what happens if they are not integers? Well, the floating point operations are always like lengthy, and the data will also become lengthy. So what happens is that your microcontroller cannot sometimes handle so much calculations, and it tends to slow down a lot. So what we do is quantization. We'll just make all the values integers, floating points. This doesn't make much of a variance when the for the weight when your weights and biases are in higher values. So this helps with size, and it helps with portability. So since some devices cannot handle floating devices, some devices can only support 32-bit operations. So that will help with portability. If we quantize the model, we can use it anywhere. Latency in sense, since some models, all the microprocessors need a lot more power when handling floating point values. When we quantize it, there are no floating point values, so it's much more easier to handle the data. And microcontrollers are found to be up to 2 to 3 times more faster when they are quantized. Size, that's a small benefit over here. Since the floating point values are removed, we can save a few kilobytes of data at about 10% every run. So the quantization is an important part. This speeds up your microcontroller by a lot. So like steps to implement a TinyML application is the same thing. Decide an idea, decide on the components. So like you have to find the right microprocessor at the same time. So Arduino BLE33 is one of the uh, microprocessors which can support a TensorFlow TinyML. So like that can be suitable in some instances. ESP32 is another device which can support TinyML. This can also be used to support in other instances. So you'll just collect data and train a machine learning model, build the application code, upload the code to multi-controller. So this is the basic flow of my application here. So it's when you make an application in the for a microcontroller, these are the basic things. You need some variables for having error reports, input and output tensor interpreters, and there's some specific functions which we'll discuss in next class. And there are some loop functions which run again and again so that it produces constant output. So our final thing is like we have to make an LED which can change as per sine curve created by our model. So like why can't we just run a sine curve? That's not ML. So what we'll do here, we'll make a sine curve, add some distortion to it. So the data looks raw data and it has so much distortions. We'll see it later. And so at the end we should make a LED which has the ability to blink, as you can see here. So you can see the LED blinks according to the power of sine wave here. So this may not seem so significant right here. Like so, we are making a LED blinking on a sine wave. So like if you use a temperature sensors, for example, you take all the input from a temperature sensor instead of the sine curve. We'll get a much. What happens if there's a +1 degree, -1 degree? The temperature won't be constant. So if we can process it, we'll get a constant graph of temperature, which is more accurate than sensor reading itself. So that's what we are trying to achieve technically. So sine curves exhibit some similarities to other projects. So we will move on to Google Colab. Here we'll have a code along session right now. I just sent a link to a collab file right now. Can you guys open it? Just react to it if you can. Okay, so after opening the collab file, just go to the option called file here. I'll just share it. So after opening it should look something like this here. So just go to file, go to save copy on drive. File, save copy on drive. You'll just create a copy over here and it'll open a new pop-up window, or it'll request you to, it'll just show it, you saved it a file. So now you can edit, since you saved this to a drive, you can edit this file, you can code along with this. So any questions till now? So no doubts. So we'll just start with the code along right now. Okay, so first we for TinyML code, we need a few libraries which you have to import into the Python. We'll use Python for ML because like Python is an easy language to learn. It does not have like so much of a fixed syntax. So like it's much more easier to access and work with. So we'll just start with importing libraries in Python. So we'll need a few libraries at first. We'll need NumPy for plotting. We'll need matplotlib.plyplot to plot all the different graphs. We need NumPy um, for doing different functions such as split and generating random values. So we'll need NumPy and we'll need TensorFlow too. So import TensorFlow. And we'll also import the NumPy. We'll import matplotlib. As PLT. And we'll also import a math library so that we can access pi values. This is not necessarily if you know if you can type pi values, it will be enough, but we'll also import math anyway. Okay, so we have imported all the required files. It's not necessary that you need to run at every step. You can run everything combine it later. So since we are training a network, we don't have any data to train on. So what we will do, we'll generate a sine curve and we will use the same data to machine learning. So since like using a sine curve to generate a sine curve model doesn't make much of a sense because like we already have a sine curve. So what we will do to give an like an in a real world situation, our data will have a lot of distortion. We'll also add noise in further. So we'll now just generate a sine curve right now. So let's say like we can't generate a smooth curve. We'll just take a point, 1,000 points in between some points. So we'll just take samples. Samples is equal to 1,000, for example. And there's a function called seed in NumPy and TensorFlow. So basically, what seed is like when you enter a certain number, a certain output is always received on the other end of the function. So when you use the seed function, for example, let's say seed is equal to 1337. If you generate random numbers using the seed, and I generate the random numbers using the same seed, we both will get the same random numbers. What's the significance of this? Even though numbers are random, we can check whether our data set wrong. We can compare it side by side. It will be more easier for analyzation or like for error correction. It can be useful and further. So we'll just set the numpy seed. NumPy seeds as a random. What the seed is like, we took here 1337 for example. We'll set the same thing. So basically what it did here was just set numpy.random seed as seed, TensorFlow.random set seed is equal to seed. That's all. This two lines signifies. And we allow to generate all the values for x function. So we'll let's just assume we'll just simulate all the values from 0 to 2 pi for a single sine wave. So we'll just simulate x. Let's just take the function as x values is equal to np.rand random. Now this random functions has the set seed, so we'll generate the same seed. Now np.random.uniform. So if we give a certain interval, this function np.random.uniform will generate a random data sets with equal interval. So we'll use this uniform low. So lowest value should be 0, and our higher end should be up to 2 pi. So we can't type pi. So here the math import math we did right here. So this part comes in handy over here. So you can just do a 2 star math.pi. So math.pi represents the value of pi here. And the size of number of elements to be present within the random is size is samples. So we need 1000 elements, right? So this is the size of samples. We'll just shuffle it once so we can be sure that this is entirely randomized. So we have shuffled all the values, and we'll also need so these are the x values we take at a random point from 0 to 2 pi. We can also need y value, so we can define y values will represent the sign of x. So we'll define y value is equal to np dot sign. In numpy that's sign function, so np dot sign of x values. So y values is the sign function of x values here. Okay, now we have assigned a y value for every single x value for 1000 x values. Now we can plot our graph. So plt dot plot x values, y values, and we also need to define the color. So like let's just take the color to be green. Green means g dot. The g dot represents the dot function in green. So you can see the sample data being generated. This is the current data. So we can make a ML model with this, but this is not this is not what we want. We need a random data which has noise in it, a data which is not consistent, and we'll develop a model which can remove all the noise and give us a solid data. So like this is already solid. So what we'll do is just add random noise. adding random noise will give like example for real world data. This is like closer to real world data than the initial sign graph. So are you guys following up till now? Are you guys following till now? I guess. Yeah, I'll just show the part above once. So far we have just imported some basic libraries: TensorFlow, NumPy, Matplotlib.pyplot, and Math library. So these 4 libraries will be helping us. Then we have generated a random data set, uh, which basically like we can't get real values with sensors right now because you guys don't have components. So what we did is we just generated a sine curve for now. We just generated a sine curve and we are going to add noise now. So it represents somewhat closer to a real world messy data. So how to add noise here? So we'll just add to add noise. You can use NumPy's random function. So y values is equal plus is equal to same as y plus values is equal to some function is y values plus some value. We if y values plus is equal to x means y values is equal to y values plus x. So we'll just continue here. Y values plus. We will just add a random multiplier so that we'll get some. Now the data is from 0.1. So that's what this multiply 0.1. Then multiplied by the randomizer. So like this function randomizes and multiplies 0.1 between the y values. So this function the y values vary from -1 to 1. So this function adds anywhere to this y value from -0.1 to 0.1. So now we have a scattered data which has a small variance, and when we try to plot this data, so we'll just plot this data once again. Plot x values, comma y values, and also we need to represent the color. We'll just put another color. Again, we'll just continue with green dot, and we have to show the plot. Plt dot show. So you can see now the data is scattered all over the place. You can see the data is like too congested because like since we gave 1,000 samples, it seems at the certain point there may be 2 points. At the certain same x value, there may be 2 different y values, but that's not the case. The data is just too close. It looks so scattered. This is how real world data looks like from sensors. Probably not this much variance. So now we now have a data which can represent the close of what we get from machines. Now we have to split to train the model. You have to split the data because like when you're training the model, you have to need to take a certain part of the model away and call it validation, and another part to test it. Basically, training data will run through it. We'll just train the model with training data, and the validation data, what it does, it checks whether if the certain part of data like gets correct values. So like if our model is overfitting, like when what happens is that it tries to train so accurately, it also include all inaccuracies. The validation data will be having high loss errors. That point we can realize the model has overfit, and we have to reduce the complexity of the model. If the validation data is the model is underfit, what happens? The validation data will show low, will also show high errors. It's relative. Training error data will also show high errors. That point we can realize the model is underfit. I'll repeat again. So like we have to split the data into three parts. So training, validation, and testing. Training will train the model. With validation, you can check whether the model is underfit and overfit. With testing, you can find how much whether the model is working properly or not. So this is the so we can split the data out 80%, 10%, 10% too. But for this model, the ideal amount is found to be at 60% and 20%, 20% for training, validation, testing respectively. So now we have to make a function which can split the data at the 1000 samples, and we have to split this data. Since we have randomized all the data here, we don't need to shuffle it again. So we just shuffle all the x values. So we'll just split the data randomly. We'll just take 2 points. The 2 points will be at first 600. There should be a split at the first 600 between 600 and 601, since there are 1000 samples, and there should be another split. So like the 1000 data, so there should be it should be split in proportions like 600, 200, and another 200. So the split should happen at the first split should happen at 600. At 600, second split at 800. So when the second split between the first split and second split, element exists for 200. At the end, there's 200 samples exist. At front, another 600 samples exist. So we'll use. So first, we'll just rename it as train first split one. Anything we can name it. Split one is equal to integer of 0.6 into samples. So basically, what we did here is we just multiply 0.6 with samples because our training data first split should happen at 60%. So why I add an integer function? Because floating point returns floating values. So we just multiply it with the integer again. So we made it integer, so as to not give us some floating point values. So similarly, split 2 happens at 800. So we'll just define it as we'll just add the training as the 600 with the split one. So we can do it like 0.2 0.22 samples plus we can add a split one. So we have identified 2 points where we need to split the data. Now we'll get to the splitting part. So we'll just name it as they will name the x values as 3 different parts. So training data will be x train, x validate, x testing, x test. So these 3 will be split using a function called np.split. So np.split takes a sample and it just splits at the certain points where we give the data where we need it to split. So we need a split at 600 and 800 to give it 3 different parts of 600, 200, 200. So we'll just do np.split. np.split off, we have to split the x values. So x values at the parts I use square braces here. At part split 1 and split 2. So now what happens is that let's say if it's for example, let's say if there are 10 elements here. This is our sample. The 1, 2, 3, 4, 5, 6, 7, 8, 9 is our sample. And if we give split 1 and split 2 as, for example, let's say 2, 1, 6. After second element, there will be a split here like this, and after the sixth element, there will be split like this. So this is what happening. This is exactly happening here, and we are just doing it on a larger scale. So now we have split our data for our requirements. Now we have to so like we have now data. We have created some data. We have added some noise to represent the real world data, and we have now split the data according to the requirements. Now what we have to do? Now we have to start training our model. To train our model, we have to design our model. So the model is what uh, the neurons, several different neurons consist of a model. So we'll design a model. So this model is going to be basic one. So it will have 16 neurons in the a single input to the function. So the y value is the single input. The single input y value will go through. It will run through 16 neurons. I guess it's a mistake here. So it runs through 16 different neurons here, and is on the way and using biases and weights, a certain neurons will be activated according to the y value here, and it gives a single output to represent the y value again. So our model is going to be look like something. A single neuron splits to 16 different neurons and again joins to a single neuron. So now since I'll just add. So add a code block here. Now I think this is not that right. Sorry. So after training the model, there'll be empty code block. We'll just create our model, our required model here. So we will use TensorFlow right here. TensorFlow is used to design models, as you guys know. So we'll import some new functions from TensorFlow. TensorFlow.keras. Keras is used for importing models here. So we import a function called layers. Layers will just help us to compile the model here. We'll just name our model model1 for now. Model1 is equal to tf dot sequential. So sequential is a function. This just creates a linear neuron model. It's not complicated. It's just a basic. It helps us create a basic linear model, sequential. So since you're designing a linear model, you have to specify that this is a sequential here. So now you have to start adding the layers to the models. So we'll just add the first layer, model1 dot add. I'm sorry, model1 dot add. Then we'll define the layers. Yeah, then now we are adding a layer. Plot dense. Now we'll add now number of neurons in this first layer, which you assume from the input. We are just splitting into 16 different neurons right here. So 16. Activation function also is required to like activation function is required to activate the neuron and give it a certain value, and so it passes to the output. So we will use activation is equal to relu. So relu activation is this is just a piecewise function. It's 0 if it's negative and it's the same value if it's positive. So that's the relu activation here. And here the input shape. The input since it's the first layer, the input is always comes from a certain point. I'm sorry. The input always comes from the single point. So input shape. In this point, we need only one input for y values. The sign value is the only one input possible here. So the input shape is 1. So we have defined input shape here. So we didn't complete the model. Okay, now we have to add the ending a single output layer. So we'll just add model underscore 1 add layers dot ends. We'll just add one. Adding a single one will result in an output from here. Okay, so I didn't add. Input space is equal to 1. So it's like input is a single value, it's not an array or like a series of values. So they have defined that properly. And now since we have now we have created an array model which first it takes an input of a single value here. It goes to an activation function and it goes to 16 different neurons in this case. So after going to 16 cases of neurons and getting processed with bias and weights, it goes through a single function called output function. This output function basically defines our sign value here. So since we have made a basic model here, so we can start compiling this model. So model1 dot compile. Model1 dot compile is used to compile. Now we have to use an optimizer function. Uh, Optimizer function to compile the model. So it's basically an algorithm used to optimize it. It's beyond our scope right now. Optimizer is equal to RMS prop here. And we have to use a loss function. So this loss function is a function that tries to reduce the loss, which we'll see further. And there's also a function called, we'll use a mean. We will use loss function MSC and for metrics. So the loss function is mean squared error. So we'll use this loss function to get the difference between the predictor value, and this function runs to and tries to optimize so that can reduce the you try to operate with the weights and biases so you can reduce the losses here. And similarly metric functions also operate here. Here MA stands for mean absolute error. So these metrics will help us calculate. So now we have compiled our model here. So we need to know how the model looks right now. So we can use model one dot summary. I think I made some errors. Summary should have brackets. I forgot the bracket, so just note it. So I have now made a model with the dense function. So uh, the first input gives an output of 16, and the second the through the first output will go to another layer of neuron to give a final output of 1. So these 32 parameters represent the 16 weights and 16 biases, and these 17 parameters represents 16 weights and 1 bias. Yeah. So now we know what's the structure, basic idea of the structure. So basically, the single neuron, it goes to 16 neurons and it goes to another neuron here. So yeah, we now we'll train 49 parameters here. When we start training, we'll train these 49 parameters so that we can get weights and biases which can approximate the values here. So we'll just start. We'll train our model in the next code block. Well, let's just name the model history. Let's just model the history one is equal to model and one dot fit. A fit function is used to train. We are using training data of x and the training data of y. We will use training data of x and training data of y. Now so we'll also use an epoch function. Epoch function, the basic represents how many times you are training model after running each of the every single sample to the model. So like if you want to train the model every 2 times you run a y value, you need to give, since you're running 600, we'll give 300. Since you can run it every time, I'll just give 1,000 or some random value here over 600. And we need also add a batch size. Guys, I'm sorry, I made a small mistake here. In the splitting the data, can you just come to splitting data once? In split the data, I just split the x values, I didn't split the y values here. So like just copy the function here once. So since we split the x values, I just forgot to split the y values. So splitting that, we'll just split the x values and y values correspondingly. We'll also add one more function. Assert function usually returns. So if the sum of all the values are correct, it will return the sum. So the sum of x train and sum of x validate and sum of x test adds up to samples. So this assert function is basically uses that if the total of the train validates split data is not 1000 or the sample size here, it gives an error, assertion error, and we can find where it's the error. So it will be easier to find. So this is the part here. Now it works. Batch size represents the number of times after which we need to update the Bayesian bias. Epoch function represents here. Epoch function here represents how many times we need to run the function. So we'll just use the training data here. So after fitting the model, we just need to validate. So we'll use validation data too. So we'll also add the validation data here. X validate, comma y underscore validate. We'll just run the function while validating our validation set. So we'll try to simultaneously balance the loss and the validation loss and training loss here. I think I made some mistake. Just wait a minute. I'll just check it.
Santosh,
Yeah.
try running that X train cell again where you first defined
Okay.
it.
Okay. Yeah. So I think this might be the problem. Oh,
So,
that's a problem in split. So here the splitting, some problems happening here.
mm, go in that runtime and try running everything again once.
Okay, I'll just start from the beginning. Just a minute, guys. I'll come.
Santosh, there should be a plus there. Your assert function,
Yeah.
there should be a plus. Assert xtrain.size plus xvalidate.size plus xtest.size equals 100.
Okay, I thought it was commas. I'm sorry. I'm sorry for the delays. I'll just continue now. So now it should run. Okay, I'm sorry. Like I have to take size right. So x train dot size comma x validate comma size comma x test comma size. So now this part works. Then I'll just run all the parts again.
Or try epochs. Yes.
Okay.
EPOCHS.
Okay, now I made some mistakes. I'm sorry, guys. I'll just explain once again after the when it's done. As you can see now, the model is getting trained one by one. You can see every single sample is going through it. You can see the execution time. You can see the loss function. the mean absolute error and mean validation loss and validation mean absolute error. This function runs for a while. So I'll just revise. I'll just tell what mistakes I made. I trained the X sample, but I forgot to train the Y samples here. So I forgot to split the Y sample. I just split the Y sample. Assert function is used to make sure whether you split the data correctly. So we'll just X underscore train with X data. So we'll take the size of it. We'll just add it. If it matches with the samples, it doesn't show an error here. So I made a pretty small error. I'm sorry for the delay anyway. And we just run the neuron network. And here we are using model one dot fit function is used to train the model here. We'll train X values and Y values. We'll go to 100,000 different samples, but it won't go through it. And the batch size is 16 here. So after every 16 elements, there's a revision in the after every 16 elements, the biases and weights will get changed according to the upcoming data. The validation data is X validate, Y validate. The validation also takes place simultaneously here while validating. So this takes a while to run here. So now you can see the model has finished training. Now we have run through the testing data. The model has adjusted its weights and biases to adjust for the next steps. So now we can see how well the model is trained. So using this mean squared error function, mean absolute error, the loss and validation loss, we can observe how much our model has trained well. So we'll just call a CSV file. History one is the model which we named it here. History one is the train data of model. History one dot history of loss. So we just take all the loss functions. We'll just recall from the functions. We'll just recall all the loss values and we'll make it into a list or comma separated values. And similarly, we'll do same for the validation loss. And now we have to plot this against every single epoch. So we'll do right. So epoch should be like it start from range 1 to 1000. So we should write a range function here from range 1 to len of loss plus 1. So basically the range functions it just adds 1. So first epoch will be 1, second will be 2. It will go till the length of loss. Length of loss will be 1000. It won't take the last element here. So we'll just give length of loss. So we'll go from 1 to 1000. So we have another list comma separated value file called epoch. And we'll plot the graphs now. Epoch will be in the x-axis and loss function will be in the y-axis. Let's say color is blue here. and label is equal to training loss. Similarly, we'll make another function which validation loss here. Validation loss, label is validation loss here. We'll change the color to green here. You can see once initially the losses are high because the model is like completely untrained, so it doesn't know what to do. After it trains to a few model, you can see just stabilizes over about after 600. There's not much variance at all. So till 600 the model trains well. So you can see the losses are minimum here. From the losses are about 0.1. This may seem minimum, but when we go further, we can see this 0.1 is a pretty significant loss because the function just varies from 1 to the function just varies from -1 to 1. So since the graph, we can't see the graph because the first few hundred functions take up the most of the values. So we'll just skip first 100 functions. So we'll just do the same thing, same plotting. I'll just copy this. So I'll just plot the same thing, but this time I'm just starting from 100th value. I'm from 100 to the end of the value. So this function represents from 100 to the end of value. So loss also same, 100 to the end of the value, and label same L training loss. So we're just plotting the same graph, but we are just removing 100 elements so we can zoom it on properly. Okay, I didn't keep the y values. I'm sorry. So for both now training loss and validation loss, the graph starts from 100. You can see the validation loss is clearly more than training loss. This indicates there's a severe uh, and there's a severe overfitting of model. So the model has picked up so much. It's a related term, underfitting and overfitting. So like when the model just goes to every single inaccuracies, it seems to be an overtraining. In this case, we can, since our training loss is so much lesser than validation loss, we can only assume that the model has overfitted right now. So what happened? Like we may have trained the model here too much. It seems. We'll also go into further metrics. So like after the loss from 600, the point is mostly stable. The losses averages about 1.55 here. So the 1.55 is like a constant line over here. Yeah, it's all 1.5. You can assume the losses. So we'll also use the we'll also use the mean absolute error function. So okay. So mean absolute error function can give us an idea how much the function has varied from the further value. So it's the same. We can use the same history function. So history1 dot history of mean absolute error validation mean absolute error is equal to history underscore So we just call the mean absolute error and validation mean absolute error here, and we just store it into a list. Now we'll plot this similarly. I'm just going to copy this function. I'll just change it from loss to MA here. Okay, my screen is not visible. It seems to be. Is my screen visible? Something else.
Has the screen invisible? No, no.
Is my screen visible now? Can I just continue?
It's visible.
Yeah, I'll zoom it in if you can't see it properly. Okay. Okay, so now I'll do the same thing for, I'll just copy it here. I'll just change it to mean absolute error and validation mean absolute error. So it's training MAE, it's loss MAE. You can see the absolute error is about 30. You can see it's between B0.3 to 0.315. So this error is pretty big because we got a 31% error. So it's like so ridiculous, right? Like this model cannot be useful for anything. We'll just print how the sine graph looks, the predicted graph. We'll just create a predictions. We'll just recall everything from the. We'll just take from the model one. We'll just predict the train data here. We'll just plot x test comma y comma blue. The label. So test data is the actual data we got from the machine. So we'll just name this as actual data. And x predictions and y predictions are what we x train and predictions are what we got from x test y test. We are just using to test it with the this is the data which we had initially got. We didn't run this data through the machine learning model, so now we have fresh data to analyze whether it suits it now. So now the same training data we'll use in the predictions here. What the predictions are given for the training data. So we'll just label it as red or dot equal to predicted data. Now I made small. Okay, it's predictions. Identify. You can see we didn't get anywhere close to a sine curve because it could be a multiple of reasons. So here we gave a basic model. The model could have been undertrained. There shouldn't. You can see it is pretty underfit. Like it didn't take the data very well. So this model is pretty underfit. This could be because we didn't give sufficient data. This could be also because we didn't train our model we didn't give a proper structure, enough complex structure to our model. Since we went through 600 data, we can safely assume that we are given enough data for the model to train on. The lacking in this part is that our model is not complex enough. Like our model is not complex enough to be trained here. So we'll train a better model now, which can actually predict the correct values. So we'll just go through everything once. So far, what we have done. So we just imported some basic libraries. We generated we'll take 1,000 samples here. We just set a seed. We just set seed so that we're analyzing if we run the program once again, or when we practice it, will be easier for us to learn. And we'll just shuffle the values to make sure it's correct. And we formed y values are the sine values of x, and we formed a graph. Now we add a noise so that it matches the real life data, and we just split the data into 60, 20, 20%. So first split happens at 600, and the second split happens at 800. The second split happens at 800. So X-train is the largest, which contains 600 data value samples. X-validate has 200 samples. X-test has 200 samples. So assert function is used so that the sum of all the train valid test is equal to samples, so that there are no samples left behind. So after that, we started designing a model. This model has uses ReLU activation. ReLU's base piecewise function is 0 if it's negative, or on the same number it's positive. It takes a single value input. It goes to 16 neurons. It passes to weights and biases. It calculates. It doesn't calculate here exactly. And after going to the 16 neurons, the 16 neurons add up to one neuron. That is pass to all the 16 neurons will go to single neuron. It will pass to weights and biases again. So now we'll just compile the created model here, and we just print the summary so we can understand it better. So one single input is here, input shape 1. It goes to 16 neurons, and it goes again comes to one neuron. So the parameters are 49 parameters. The parameters can be split as 16 weights and 16 biases between the first input and 16 neurons, and 16 weights and one bias from the 16 neurons to one output. So now we started training our model 1.fit. The history, all the values of model 1.fit is stored in the history underscore 1. So X train values are given, Y train values are given to train the model. So the batch size is 16. It goes to 1,000 different values. The batch size is 16. So after every 16 samples run through the model, the biases and weights are adjusted here, the parameters, and the validation also takes place simultaneously. Validation rate of X validate, Y validate. So after that, loss means we're just calculating the losses here, the loss functions. The loss function comes at 0.1. So the loss is 0.155 because we can find that the validation losses are higher. The validation loss is high to a variety of reasons. Usually it represents the model as overtrained, but this is not the case here. It's a relative term, so it may not be accurate always. So mean absolute error use the difference between the predicted value and actual value. So the mean absolute errors are here actually high. It's so high that it doesn't make sense. Even we just gave an error of 0.1, right? Should be around 0.1. It should be right. So we can see the validation data is all over the place. So it's not the right one. So when we print it, we can see the model has it has terribly underfitted. Excuse me. It is mainly due to the reason the the model which we have designed is so basic it cannot compute a sine wave. So any doubts till now? If you have any doubt, just post in the chat once. Okay. Guys, take a 5 minutes break. Then we'll start with. Then Pratyush will take over, and he will teach how to design a proper model, which can actually predict the sine values properly. It's a more complex model. So 5 minutes break. We'll all meet back at 10:40.
Hello guys, hope you can hear me. Can someone confirm if I'm audible?
Yes, sir.
Okay.
You're audible, Pritesh.
So 1 minute, I'll share my screen. So this is where Santosh stopped, and if you can see this graph here, our predicted graph does not look like a sine wave. So we are just going to add one more layer of 16 neurons in this to increase our model's accuracy. So let's just go there 1 minute. So here we were making a model. We are just going to add one more layer here. 1 minute. Layers. So if you are attending our session yesterday, you might know that adding a one more layer will increase our accuracy and make our model better. So it might understand the complexity of this problem, which our model currently fails to understand. We'll again use a ReLU function only. We don't need to define what shape our input will be in, because this layer is going to take input from the layer before it, which is this one here. So we don't need to define shape of our next input. And let's run this one. Now we'll just train the model on X train Y train. If you can see, our loss is really less right now. So adding a layer does make a significant difference in ML or deep learning models. So we'll just have to wait till all these epochs are completed. Uh, like running this data and all through a model takes a lot of time. So that's why we are using Colab notebooks, since now it doesn't take up computational power. Otherwise, on our own computer, it would have taken a lot more time. We'll just have to wait till it ends. Okay, almost there. Okay, done. So we've got both loss and mean absolute error for both of our training data and validation data. Now we are going to see our graphs. First, we are looking at graph of loss, which was mean square error, if you remember. if you see now, our training loss and validation loss are almost overlapping. So this is thanks to that additional layer we just added. Now to take a better look at a graph, we skipped first 100 values and we plotted the graph again. Now you can have a clear look at the graph here. This is, by the way, loss graph, that mean square error graph. Now we will look at our mean absolute error. This is also a type of loss only, mean absolute error. Training data validation. If you can see, our loss is almost overlapping. So this is a good sign that our model is not overfitting anymore. It's giving almost same result for both training data and validation data. Okay. Okay, we made a problem. Now let's look at this final graph. As you can see, our predicted data is almost a sine wave now. Now, this is not completely perfect, if you can, because it's not a smooth sine wave. It has some edges in the graph, but the model isn't perfect. But it's good enough for machine learning. One of the important part of machine learning is to know when to stop. This model is good enough for our case, which is to make some LEDs blink in a pleasing pattern. So this is a new model. As you can see, our accuracy has increased exponentially by just adding one layer. If we added one more layer, then it might look uh, exactly like a sine curve, but we would need that accurate graph. So now uh, we are going to convert a model to a TensorFlow Lite, because to upload it on a microcontroller, we need it in TensorFlow this format. So for converting it, we'll by the way convert it both with and without quantization. Quantization is a technique that reduces the size of our model, because microcontrollers don't have that much space. We need a model to be very small, and after quantization, weights and biases changes, and well, it save memory, but it does not even impact on accuracy. So to convert, we'll first make a converter. First, we are doing it without quantization. TensorFlow.lite. From Kera's model. This takes argument. This as an argument, it takes one model. So model underscore one. Now we are going to convert this model here after making converter, and name it TensorFlow Lite model. So now we'll save this. Save this model in a disk, and we'll name it sine underscore model, not TF Lite. So we have converted a model, but this one was without quantization, and that possibility does exist that this one might not work on a microcontroller. So now we'll convert it with quantization. So first we'll make a converter again. I'll just copy paste this line. Then we'll one way of optimization, one way of quantization is to optimize it. So we'll use optimization. Now we'll make a generator which gives our all x values, because to create a quantized model that runs as efficiently as possible, we have to provide a representative data set. Now a representative data set contains full range of input values that the model was trained on. So we'll make a generator which will give a representative data set. So let's just name it representative data set generator. So we want every value in our input of the data set on which our model was trained on. So we are going to run a for loop on x underscore test. Now we want every value to be inside a 2D array, because TensorFlow understands a 2D array or NumPy array better. So I will convert the model now that we have quantized a model. We'll save this one also in our disk. Open. I can just copy paste this. So we have converted our model into a TensorFlow Lite model from TensorFlow model. And okay, Now we'll test both the converted models, like to see if I just told before this that even after quantization, the accuracy of the model is not affected that much. So just to test the theory, we are going to test both the models. So before testing, we need to, because now these models are TensorFlow Lite models, we'll need an interpreter to interpret them. So let's just make one interpreter for both the models. So sign underscore model. Interpreter. And this interpreter is for a sign underscore model and for that quantized model. Now we will allocate memory to both of our models. For that, we'll use allocate tensors. Sign model dot. Now that we have allocated spaces, to operate on this efficiently, we will need indexes of both input and output tensors. So to find index, we can use get first. Okay, just see I'm doing it here. Sign underscore model. In, for input index, I'm naming them input index only. So now I'll use get input details on sign model. Get. Now this function will give us all the details about the input, but we don't want all of them. We only want details about indexes. So for that, we'll use slicing. So one was input. Next one is sign output. We want output index as well. And here we will use output detail. Then we'll do same thing, but this time for quantized model. So and here as well. And this one is output. Now that we have indexes of both input output for both of our models, we'll make an array to store the results. So for that, just make one array sign predictions. This is an array. Quantized model as well. We'll make one array to store our predictions. Now we'll run interpreter of both the model and store the results in their respective arrays. So for that, we'll again need for loop, which will run on all of our input data in x underscore paste. We'll again make one 2D array. Now this is a 2D array here. We don't really need to mention data type, but it's a good practice to do so. Now that we have our input values, we'll write the values. Now we'll run inference. Now to get our predictions, we will use sign underscore predictions function. And we'll append these values in our array. Now we'll do all of this stuff again for a quantized model. So from here, we made a mistake here, guys. We don't want quantized value. That's fine, I guess. Now we can just plot the graph and test our results. But before that, we'll clear all the previous graph using php.clf. We'll give title to a graph. Let's just call it comparison. We'll plot both the graphs. And let's go. We'll give this one a label, a factor. Now, but instead of y-test, we are going to use the predicted values. And we'll change color as well. We'll label this one as, let's say, original OG predictions. Now we are going to plot our sign model and a quantized sign model. And we'll change color again. Now let's call this one as Lite predictions and Lite predictions. Okay. plt.legend shows all the labels in the graph, and this plt.show. Okay. X value t dot x underscore value is not defined. Just 1 minute, guys. Looks like there's some problem. So I'll take this entire code and let's just use it here. Again. So it should work now, I guess. But this is going to take some time because it will run those 1000 epochs again. It's here again. I hope you guys were able to follow. We did nothing. We just first added one additional layer, which increased the accuracy of a graph, and then we converted it to a TensorFlow Lite model because we can't upload it as a TensorFlow model, and we converted it both in a quantized manner and unquantized manner. We have to quantize because we don't have that much space on microcontrollers. So quantization decreases it in space without affecting the accuracy. And right now we are just testing the statement about accuracy. And don't worry about the coding part. We'll share this notebook with a well commented codes. Still on epoch. Okay, we are done with all the epochs. We are still facing same error. X underscore value is not defined.
I think that's a mistake in your cell. You wrote sign as SIN.
Where?
That cell, sign quantized, sign model,
Yeah.
SIN.
No, mistake is actually in this. They are saying X value is not defined. Acha, wait. X values is defined. Sorry, I'll just change this one here.
And even sign model or set tensor, SINE.
Oh, okay. Thank you, Sanjay. It has no attribute predictions.
It's not dot
Okay,
prediction,
it's
it's underscore prediction
underscore.
and then
Yeah.
append function.
Okay. And then dot Acha again sign. Interpreter object has no attribute predictions. Test. What's the problem here? But have shapes 200 and 601. Okay. You need to see this one. RO label. Same first dimension, but fixed out at end.
I think you can comment that line. That line isn't really needed.
No, then it will show error in next line as well.
No, not as
Acha.
specified.
Okay, wait, let's try. If some made some mistake in shape somewhere.
I think we shall stop here. Tomorrow we can
Okay,
check it.
no, just we made mistake. We need this one before that one. That code. Okay, we'll see this one tomorrow, guys. We can't figure out right now what where did we make mistake. So, but I hope you understood how we changed, how we increased accuracy, and we'll prove our statement tomorrow about that after quantization accuracy is not affected, and also we'll see blinking LED tomorrow with using this ML model. So hope you come back. Hope you guys come join again us tomorrow. We'll end this session here then.